Hello boys and girls. In this video I'm trying to raise our cultural capital again and talk about books that I like, that I recommend, that I freely shill, that also related to other content on this channel. In particular, I have been reading this fine piece of history of science and mathematics and physics. In particular, it's called Zwischen Zwei Disziplinen. Sadly, this is 400 pages. It stems, I think, from the dissertation of the woman who wrote it, Martina R. Schneider, German mathematician, and I think now mostly, if I understand it, historian of science and mathematics. It's called Between Two Disciplines, that what it relates to, and it stems from her PhD thesis, if I understand it correctly. And it is a book about this important guy, B.L. van der Waerden, and everybody on this world has different accents, and some people tell me I should not put my ugly fat face into these videos. Sorry, I can't do that. And people point out that I have an accent. I can't do too much about that as well. Let's just say I am aware that people pronounce things differently, and I'm not Dutch. This was a Dutch guy. And I will say Waerden, which would be the German pronunciation. If that fails, misses the mark, I say sorry for that. But his name is van der Waerden. So this guy is not known enough, really. He was super influential, in particular in algebra in the 30s, 40s, 50s. In particular because he wrote a very famous book called Modern Algebra. He was a student and colleague of many of the famous people from that era, and he's kind of summarized Noether's recent work and insights and other people around that time. He was like the young guy picking up on modern algebra as it arose, and he wrote a super famous algebra book. But apart from math, he was also a colleague of Heisenberg and in contact with a lot of people. And in this video, I will talk about the early history of representation theory that goes with that. So, in previous videos, I talked about Lie-algebras in various videos. Presented some books, and in particular I talked about the representations of the quaternion algebras, like the standard Hamiltonian quaternions and other quaternions. Goes in the quadratic forms direction. Then more generally you would speak of, I don't know, Clifford algebras and these kind of things, and their representations. I talked about matrix representations, and this is all extremely important in many applied fields. So I would say physics in particular, but at my job I do computer vision, and even though the physics in the sense of force fields are not that relevant there, you still want representation theory, and even if for implementations, even if you do high performance calculations, as soon as they are spatial, as soon as you talk about Hamiltonian quaternions and use these representations for representations of rotations in space, this is related to in the last video me talking about rigid bodies in space moving around, how you represent it in a code. Then it's all about representations, how do you approach that, and the whole kind of spiel manifested, let's say around 1870, with people systematically starting to study group representations. So I will talk a little bit about this book today, but mostly just the first 70 pages, which is actually the stuff before it actually talks about the main guy here. So there are 70 pages, just preparation that gives context for his work when he was a young guy. And that spans, on the one hand, pure math research. I will, shout out some names. So Frobenius, Burnside are there, like some major players. And then how that got immediately picked up by some physicists, in particular Wigner, when they tried to incorporate it and use it in the emergent theory of quantum mechanics, which was super new at the time, but arose, let's say, at the end of the 20th century, so 1900, there somewhere in the first years, now 120 years ago about, roughly. And so in the second half of this first 70 pages of this book, they talk about just quantum mechanics and the major players. First the general history, and then how group theory played into that. And I really like what I read so far. So I'm not through with the book. I will not talk really about the guy himself today, if there's interest, or if I think it's noteworthy and easy to summarize. I will also talk about the character himself and what he eventually did. But in this video, it's about representation theory and a little bit of quantum mechanics. So that is what the handsome fella looked like. Okay, of course. Often in these videos, I go through Wikipedia pages so people get references. You will also find the links in the comments. And with these types of videos where I reflect on some books, since I know that not just mathematicians, not just physicists, also some computer science guys watch me. So I will include some basics and include some basic Wikipedia articles. And if that's boring, I'm sorry for that, but I guess the audience is too broad and I don't want to cut off people completely there. He wrote this book, Modern Algebra. Here, I'm not sure what the first release was, but this is like the second part of this algebra book or book series or volume. And here this is dated to 1940. Might be that it was certainly written or even released a little bit earlier. This is the book, the famous book I talked about. And there's also, and I recommended this on this channel before, there's also another, I think even thicker, history book by probably somewhat famous historian of mathematics called Modern Algebra and the Rise of Mathematical Structures. So this is a book which really covers the development or the conceptualization of what algebra actually is or what it means from Galois to basically to Grothendieck. Sorry again for my pronunciations here. So a broader time span than we have here. Little bit broader, but this book I really recommend. Like these historians, they I mean, I'm not a historian. I don't know. I can only imagine it. It has to be that from the way it's written, they go into detail on studying basically the volumes of papers that the researchers they investigate wrote and how they interacted, study other historical material, and then if they are good, then write it down in a fashion that's not just there was this paper summary in one line or like one paragraph and then the next paper, but kind of actually work out a coherent story and interaction, and then doubt some statements and see if it comes together. And in any case, this modern algebra book, which starts with how group theory was came about, which problems were meant to be solved, dealing with polynomials maybe, and then how different important figures pick that up, and then you get to know some other important people. In this book in particular, he talks about Hilbert a lot, and he also has a book, I think explicitly, there was probably the pre-runner for the modern algebra book. He has a book on Hilbert where he talks about Hilbert's approach to trying to axiomatize physics. And yeah, I highly recommend this book. I really like that one, but I think this one is also like must read. So yeah, that is the book I'm talking about. I think there's no English translation, and there might never be one. Although let me skip that for a second. The woman who wrote that book, the German, like I looked her up a little bit. She's now, in the history of math, I guess, department of the Johannes Gutenberg University in Mainz, a German city. And I think to have read that while writing her dissertation, she also, moved around, gave conferences in the names that always come up in the German math community, Oberwahlfach, and then she gives talks, and I think she lists and also like people who helped there. She lists in the early in the book who helped her out and who gave information, interaction. For example, she also lists the Corey guy, so I guess this is a more or less closed circle of historians there. And she's now in this history department, but if I understand it correctly, she studied actually pure math first, if I recall correctly from what I skimmed over. And you see it also sort of in the book. I mean, in the book, she freely uses math vocabulary and also the language sort of that the people like even the quantum mechanics people that she talks about used. Of course, she translates some, and she also points out when something is translated to modern math language. But this is a little bit, I would say, in contrast to the Corey book, the book of the modern algebra and the rise of mathematical structures. That definitely didn't have like literally math equations in it. So it's not like this book is not filled with mathematics itself, but to show here quickly, so there's an early one on a chapter on Frobenius papers on representation theory of permutation groups and so on and so forth, and you can see here maybe that there are some equations like coming up and during the text, and this is not necessarily the case in this history texts. Okay, so that's that. I looked up, of course, this van der Waerden guy, right? He is not here. I mean, there are mathematical concepts named after him. If you study math, you might come across. If I recall correctly, the Wikipedia article has, let's go here. I know there's a lot of people that actually don't know really how to use Wikipedia properly or what you can do there. What is always helpful is if you're on a site and want to know related concept, then you can go to here, what links here, and then you're taken to what links there. And if you scroll down to, let's see what is there. You see related concepts of, for example, Brauer is a, the guy came up before in this channel because I talked about constructive mathematics a little bit, and he is also like a relevant person in the later life of van der Waerden, which you might see in another video. So in this case, I don't see too many concept named after him, but then they will have some, here, for example, in the see also sections. So there are some concepts, but generally, like given the amount of stuff that he wrote and how influential he was, the books he wrote and with whom he worked with and the different fields he contributed to, I would argue that he is not that well known, sadly. So that's why I'm making the video, I guess. So, sorry. Yeah, so I looked around, apart from that, and there seems to be an Alexander Seufer, I don't know if this is a German, maybe Russian, I'm not sure, author, who also more or less recently, like this book is from 2011, he more or less recently also wrote a book on van der Waerden called The Scholar and the State. I have not, I have not seen the book myself. I didn't have it in my hands. It might be even more focused on the life and not so much on the workings on it, but I don't know. If we quickly look at the, on the from the book cover page, it's quite interesting actually. Then you see this short breakdown of van der Waerden's life in a paragraph. Let me read that for you actually. So B.L. van der Waerden made major contributions to algebraic geometry, abstract algebra, quantum mechanics, and other fields. He liberally published on the history of mathematics. Yeah, he later turned to also becoming a kind of historian, as some mathematicians actually do. It's not a rare thing. His 2-volume work, Modern Algebra, is one of the most influential and popular mathematical books ever written. It is therefore surprising that no monograph has been dedicated to his life and work. So this might not be factually correct if this was already available 2011, and in the case, I have not looked it up, that book was coming out afterwards. But nonetheless, it's a German book, this one. So even if that happens to be not correct, then let's be fair here. Van der Waerden's record is complex. In attempting to understand his life, the author assembled thousands of documents from numerous archives in Germany, the Netherlands, Switzerland, and the United States, which reveal fascinating and often surprising new information about van der Waerden. Seufer, if that's correctly pronounced, this is the author, traces van der Waerden's early years in the family of great Dutch public servants, his life as a professor in Leipzig during the entire Nazi period, and his personal and professional friendships with one of the great physicists, Werner Heisenberg. We encounter heroes and villains and much more numerous groups in between these two extremes. One of them is the subject of this book. So now, without me actually going through the biographical context of the books, you see like these short breakdowns of things that are relevant to van der Waerden. And also here, like it's mentioned naturally, a lot of things happened. I already mentioned Noether and some other German names. A lot of math happened in Germany, and also French, which is not so far from like where this Dutch man got his education from. And also it mentions people from the United States, and that is also the case then with the early quantum mechanics, because while it was developed a lot in Germany, right, from the start in statistical mechanics problems by Max Planck around, like I think, if I remember correctly, in December of 1900, like 1900. It took, like there were many people working in quantum mechanics then, it was popular, it explained a bunch of things. In particular, this book focuses on the questions regarding spectra, line spectra of atoms and molecules. And if you do, if you have a university education in physics and you have to sit in the laboratory and do this kind of basic experiment and looking through the microscope and seeing these lines, so you get some hands-on experience with this close to chemistry subject. And this is where a lot of research was dedicated into, and people adopted and representation theory as a useful method, a few of them anyway, and this is what's also discussed there. And apart from these Germans, what I want to get at is that a lot of US names are also already relevant even before the war. After the war, of course, a lot of academics and especially physicists moved over to the US. And if you go on Wikipedia pages of these physicists, then the Wikipedia will also sell them as Americans, like Einstein. So after the war, and especially since the US came out as a winner, they have had a flourishing economy, and then you have like stories of, a lot of stories of like these characters like Feynman and who heavily influenced physics in that time. But even before that, there's interaction between Germany and the US, and this book talks about this a little bit. So you have, I think Slater is a US researcher, among others, who play into the role. I will get to that in a minute. Okay, so that is covered. Yeah, so before I skip to my notes, I show you a bunch of related Wikipedia articles, and these are the ones that are also in the links below if you're interested in that. So character theory is a subject among or in group representation theory. This is how the book started when he talks about like the early guys in representation theory of finite groups, especially, although character theory also is relevant in general. This is, I guess, a super long article. To continue on recommending books, in this year, I set into a mathematics lecture series a course in the math department. I'm not subscribed at the moment in university. I just went there at 8 in the morning and I listened to that. They were going through, like literally just going through the chapter by chapter through this book, which is also very nice. So that's called the Symmetric Group, and it's a lot, especially in the first half, about representation theory, and it's just a very nice write down. You learn about characters, and if you're interested in that, and matrix representation and modules and so on and so forth, I also really recommend this book. It's very nice. So this is a book where I say, this is actually a nice book. It's like nicely written. Like I don't know how to bring that across. There are some books which you should read because they have a content, or maybe it's special in the way it's represented, or is a really good book. So there are some. So, for example, when we are going to talk about the problems that people faced in quantum mechanics, early quantum mechanics, I mean 1926, that they solved with representation theory. Then there, maybe I'll do a more statistical physics video at one point, but there's a series in Germany, and I think most of the books have been translated to English as well, by Nolting. And he has many volumes on various introductory subjects, and his books on statistical physics and also many particle quantum mechanics I really like. And they are like books. These are good books because they are good and clear representation, and I would also recommend these books. But then books like that, the Symmetric Group, this is one which is, I mean, maybe it's not as dense as it could be. There could be like even more information filled in, but it's just so nice to read. You can sit with a coffee on a Sunday afternoon, read through it, and it's kind of, I cannot really describe it, but also nice latte, nice set, and it feels structured. It feels like what it is, namely that somebody gave lectures over years and years over a subject that they really love, and then they put it into a book, and that's how it reads. Okay, maybe I praised it a little bit too much. It's a good book in any case. Okay, then also the super long Wikipedia entry on representation theory obviously is relevant here. My channel, I brought it up, is also relevant. You have to subscribe to this channel. If you are not, forward this video. So my job for this video is done as well. So then again, and I will not go into much mathematical detail. I just rant and entertain you, hopefully, and try to bring in my fascination for also the historical developments of this text. But as I said, they start with representation theory of finite groups, and then go then also in like 10-20 pages the author covers representations of infinite groups, by which I mean Lie groups, and then after like 15 pages on into the early developments on quantum mechanics, they focus on these scientists who were actually hooked by group representation theory and how they applied it, and like the premises from which they derived their mechanics. The quantum mechanics is like from let's say, at least from an axiomatic perspective, very different from classical mechanics, like classical mechanics as in what I talked about in the last video, where I talked about rigid body mechanics. And if you study rigid body, you have external, maybe in Newton's laws, external forces and these kind of things, while here you of course deal with quantum mechanical wave functions. And while this book at least early on does not talk much about wave mechanics, it mentions how the series of events happened, and it talks about wave functions, but not so much about like Schrödinger equation and these kind of things. But these objects nevertheless play a role as objects in space, and then it details in about letters, conversations between these physicists that you know the names of anyway, like Heisenberg and these guys, those who were interested in using group theory, which at the time, especially for the physicists, was of course difficult to get into as well. So that's why also some of the physicists are also kind of mathematicians, and people like van der Waerden, who were between two disciplines, which is the name literally of this book. They kind of brought the communities together. Hey, maybe that's also what I'm doing in this video. The representation theory, this was also being heavily researched. It still is, I guess, but it's especially at the time it just came out. It was heavily researched, and then it's even more difficult to get into it, because when a field emerges, it's of course much coarser. Maybe the notation has not really settled. People using different names. Like in this book, you also learn about different, names for what these famous physicists early on used in their papers when they before they talked about spin of electrons. Then some of the physicists might have written Drehelektron, so this is like turning electron, stuff like that. It's interesting, but then it kind of converges and you get a unified notation, and it gets slowly into the university. Students learn it, and but here at the beginning, they could not just open like a thick 20-year-old volume on representation theory and use that, but they were often having to read some more modern textbooks or even mathematics papers to get into that, and doing calculations, and maybe in some cases even doing calculations. And then if they have mathematicians friends, they were pointing out to them, hey, this was actually already discovered, blah blah blah. This is a lot. You have a lot of this story also in relativity theory, where there were apart from like physicists like Einstein, who strongly saw themselves as physicists and might have even said they are not great at math. There's a physical theory, relativity, but so many names like Hilbert and Minkowski, however you pronounce it, are much more associated with mathematics, right? Okay, I'm ranting here. What I want to talk about is that Wigner, this big name that has probably the most the most pages in this book in the early chapters. They were talking about wave functions, and they were interested in not just describing molecules with one atom, like some H molecule, water, Wasserstoff, German, sorry. But many particles, and then you have to speak about wave functions in space that may or may not have some symmetries, and then that's why this was a kind of angle to get into representation theory of groups by considering, well, I have these objects, and we could like postulate some principles about how they should behave in different coordinate frames and systems, and then they were studying permutation groups of the particles, and this is how the representation theory comes in. This is about 1926 when these ideas like wave functions were already established and have given answers to spectra, predictions, questions, and then it goes on to not just the finite representation, like finite group representations, but also Lie group representations, and that's why you have Wigner here being associated with the representations of SU3, the rotation group that I talked about in previous videos as well. So there are these D matrices where it's all about constructing the different dimensional sized representations of rotation matrix. I mean, you of course probably the rotation matrix in 3 dimensions, but then you jump to any other dimension, which you need as soon as you consider more particles and conceptualize the wave functions, the probability densities, or the square root, using tensor product, and then you get into the problem of having to look at arbitrary high dimensional representations of rotation of this small rotation group, this 3-dimensional rotation group, but bigger representations. And then you have, for example, here this Wikipedia page, and I think quite explicit formulas how to get these huge matrices. Okay. Then I mean, I didn't go in any depth in this channel about representation theory and tensor products and irreducibility and decompositions and so on and so forth. But these are relevant names, and this book has chapters on about 10 different scientists. Casimir is not one of them, but is also relevant in that regard, and is mentioned a little bit in the book and correspondences there. What do I have here? Dirac, who is also an interesting physicist and person. Of course, by that time that the people did the wave mechanics, quantum mechanics, like 1920 something. The special theory of relativity, which is dated around 1905, and even the general one, like 10 years later, is already established and already, like people already believe in it, has already some grounding, because how nice it plays with Maxwell's equations and electromagnetism. And so people naturally try to make quantum mechanics work already at that time with space-time according to special relativity, at least. And indeed, like just I guess in the 30s already, you get into quantum field theory as approaches, and but there are some stumbling blocks to that. And one big name is Dirac, of course, and here you have the gamma matrices of Dirac, which are representations of Clifford algebras, which are not too far away from the various quaternion algebras that I talked about previously. So here, I think the most straightforward approach to the general definition, if you know universal properties in category theory, is with this diagram. So that's basically, it's about, okay, I don't want to talk about math in this video, but I might get around viewing quaternions from the Clifford algebra angle. this channel. That was also like Fock space. Like also Fock is not explicit, doesn't have an explicit subsection in this first 70 pages, but his name is nevertheless dropped. He's of course associated, especially with this many particle state constructions, and as you can imagine, this tie closely to representation theory. Okay, gladly, I already did most of my rants and comments and trying to kind of map out the people involved. Let's quickly jump to my notes here. Gladly recited most of this already. The book is in 4 parts. Again, in this video, I'm only talking about the first one, which is representation theory in quantum mechanics, the early years. Some names that I didn't talked about is Schur, and you see, like, with these people, she goes through the papers and maybe possibly the books she wrote, connects the dots, see who best which work on whom, and who based their work on which other authors and how they influence each other. For whoever has time, I would recommend actually to go into these papers, because sometimes you get a lot of information out of that, or see actually motivations that are interesting but didn't eventually make it to the textbooks that you read now 50 years later, but might still be relevant or help you to go in other directions if you do research yourself. Okay, then of course, Killing, study, Cartan, this is all names associated with Lie groups, especially Cartan. I know somebody will point out, hopefully, what their preferred way of pronouncing these things is. I should try to pronounce it, I guess, according to where these guys came from. Weyl and Weyl, I also hear I watch a bunch of lectures on YouTube, and I have heard a lot of lectures in universities, and people pronounce it also differently, so there's no right way of doing this. Different people involved in finite and infinite representation theory. As I said, the motivation by the author is mostly with the spectra of atoms and molecules. There's a little bit more to it, but she emphasizes that she doesn't go into detail with everything. However, she always gives a lot of references. Also, when she does small summaries, which other historical references this is based on. So, if you come across this book, even if you don't speak German, and even if you don't think you will get something out of the text, despite there being some formulas, and you kind of know historically where you are if you know the math, even if you don't know the German. It's also like these books are also great in terms of references, because the historians, naturally, they actually care about their references, not like scientists and mathematicians who sometimes happen to have a useless reference section, or don't actually call out their sources as well. The exact opposite is the case with historians, so that's good. Okay, of course, they are study these people yourself, I guess. The people like Wigner worked a lot with Neumann, who also did everything in these decades. So he had his hands into quantum mechanics. Of course, he then wrote books and had a strong influence on quantum mechanics and the formulations with not just infinite dimensional matrices. I actually made a video about this at one point. But then when they went to more abstract operator approach, now from an axiomatic standpoint, if you learn math, then these things are not too far-fetched. But I guess if you live 100 years back, then people were very suspicious even of using these kind of things. And I know that Neumann's book on quantum mechanics has some even mathematical issues that were pointed out with the calculus, where later on people who worked hard on formalizing functional calculus, like made it more rigorous, let's say. And Neumann then also does star algebras and topology stuff. This is not part of the first 70 pages, but this is just lining out how Neumann keeps being relevant for quantum mechanics. Some more names there, and then the last subsection before this historical context parts and is on the Gruppenpest issue, right? So there is the strong narrative, which is very entertaining, and also true that a lot of physicists naturally rejected the use of group theory and representation theory in physics. And despite the fact that they were maybe not like, it's not like group theory was everywhere and everybody is using it, the book describes how group theory and representation theory was kind of en vogue because some big names were doing it, right? So surely Neumann, let's say, these guys, they already did relevant work, they already explained things. In quantum mechanics were established names, and they were using the math and getting into the math, and then you see there are letters of Ehrenfest, for example, or Slater, where he, in the modern, like if they had Twitter, they would be like quite aggressive towards seeing that, oh, now this, these mathematicians make everything much more complicated, mathematize things, and they are like, it's nice to read. I mean, it's German, but he reads like Ehrenfest, who will become relevant later than for quantum mechanics, who like is an established physicist and talks freely in these letters how he has a really hard time learning that, and he asks people, please can you tell me, like, and then he gets into it for a week and says, oh, I might never learn all this group theory stuff, and swears around. I mean, not really swearing, but and he also coined this word Gruppenpest. So pest is the plague, black plague is pest, and he probably coined this and used it repeatedly, like to say how the group theory is like complicated nonsense or something. And Slater, and this US guy that I talked about before, he also made some contributions, explained some antisymmetric wave configuration calculations with a determinant approach that was not as complicated or not as fresh and new as some representation theory approach, and more like to the point, and not like some of these guys they learned these newly established mathematical concepts and built then like generalized, oh, I can, now that I know the math, I can do the n particle system and and might have elaborated on to had these explanatory sections on stuff that was not like more general than was necessary. And then you see Slater and some guys saying, oh, no, I did it like that, and see this other physicist picked up my approach because the other approach is too complicated. So this is fun to read. Although Schneider, the author here, says that she argues that while this Gruppenpest approach is common lore, that it was not was not that black and white. There were many people who were interested in it, especially early on, and also people who might have been like a little bit flamboyant and complaining about it were early on also suggesting to their PhD students, hey, get into that, look at this, and so on and so forth. And a lot of people who also just didn't say anything, like might be interesting, and even if they didn't know it, it was not like a black and white war, even though there were some screaming people as well. Okay, so yeah, I had hoped that I can do this quicker, but I hope this was an interesting rant. I brought in surely implicitly a little bit of my perspective and angle of interest, and I would be happy to see another some other people on YouTube even do this kind of history stuff, especially in the subjects where I don't know the history so much. Maybe that comes out in the next couple of series and videos here. Let me know if you want more of this kind of content. This is actually, to be honest, a little bit easier for me to do, because I don't have to write down math and check math, but actually can talk a lot about stuff that I already know, and just give reference of books which I anyway want to read. So in any case, subscribe to this channel, forward this to anybody who might be interested in that, and I wish you a nice Sunday.